Okay, let's walk quickly through the complexity, the computational complexity of the Gram-Schmidt algorithm. So here's our nice Gram-Schmidt algorithm over here. And we're going to try and figure out about how many floating point operations this is going to take. So the initial normalization is probably not going to really matter. What matters is this for loop, this order n here. Okay, so for each I in 2 decay, we do this big, sort of normalization step, right? And it has, first of all, it has I minus 1 inner products, right? And each one of these inner products needs their vectors of length n, so we have to do n multiplications and then n minus 1 additions, right? So we have 2n minus 1 flops for that. Let's make a spot down here where we'll write this down. So we have 2n minus 1 flops for that, and then that's for each of the I minus 1 terms, right? So that's those. Those are the inner products, right? Q transposase. Then we need to scale each one of the previous Q's. That's this operation here, right? And there's again I minus 1 of those, and that's going to be scaling a length n vector, right? So we have an additional n times I minus 1 work to do for the scaling there, right? And then we have to add all of these I minus 1 vectors together, right? So that's another n times I minus 1, right? So we can factor out the I minus 1 and say that we have I minus 1 times a total of 4n minus 1 flops, right? And that is happening for each k, right? So the total flops in that part of the loop is, well, actually, hold on, let's do this part too, because we also need to do this normalization here. So first we have to figure out the norm, which is going to be roughly the same as an inner product, except we also have to do a square root at the end. So that's going to be something like 2n operations here, right? Whoops. And then we're scaling that vector by that. So 2n plus another n, so 3n, right? 2n to do the inner product, 2n minus 1 to do the inner product, square root, and then another n to do all the floating. And so like I said, that is happening for each n. So our total count here is something like the sum, give me my tool back, it's something like the sum from I equals 1 to k of this thing up here, I minus 1 times 4n minus 1 plus 3n. So my loop actually starts at 2, so maybe I should start at I equals 2. But thinking about it, I said, well, maybe we don't have to worry about this guy right here. But actually, he fits quite nicely into this, because if I start from I equals 1 instead of I equals 2, then at the I equals 1 term, I minus 1 is 0 anyway, so we don't do this work, which is true, we don't. But that 3n for doing the normalization, we do. So actually, if this sum here is going to include, it's going to include that first one also. It's going to get all the normalizations, and it's going to get these. Okay, so the 3n part, that's easy. So that's just going to be 3nk. Whoops. Let me zoom in a little more before I do that. The 3n part, that's going to be normal. That's going to be easy. That's just going to be k times 3n, right? Plus, now, how do I do the I minus 1 here? Well, so I need 4n minus 1 times, I can pull that one out because, again, it doesn't depend on that sum term, times this sum, I equals 1 to k of I minus 1. And that is k times k minus 1. So we end up with 3nk plus 4n minus 1 times, k times k minus 1 over 2. And one way you can remember this if you ever get stuck is, so this sum, it's going to be, in this case it's got the minus 1 on there, but it's going to be something like 0 plus 1 plus ... plus k minus 1. Maybe you've seen this before. If you have, great. Well, 0 plus k minus 1 is k minus 1. I'm going to pair the terms. I'm going to pair the terms sort of outer to inner. So then I'm going to pair 1 with, I didn't write it here, but what would be k minus 2. So I'm going to have k minus 1 plus, 1 plus k minus 2, which is also k minus 1, right? And then I'm going to get, 2 plus k minus 3, right, which is also k minus 1. And the number of pairs is going to be the total number of terms, that's k, divided by 2. So I end up with k minus 1, and then I'm going to have k over 2 of those. And there's a nice story in the book that the story is that Gauss derived this as a school child to avoid doing tedious arithmetic. Don't know if it's true or not, but it's a nice story. But anyway, okay, so now, so this is the total number of floating point operations that we're doing here. And, we can distribute out now, and the bigger terms are the ones that we care about, right? Because those are the ones that tend to dominate. So I'm going to end up with something like 4n minus 1 times k squared over 2 minus k over 2, right? Which is 3nk plus, and then when I FOIL this over, I'm going to get 4nk squared over 2 minus 4nk over 2. And then I'm going to have this other that's a minus some k squared term. But the biggest term by far is going to be this one, the 4nk squared over 2, which is 2nk squared, right? And so this thing is approximately equal to, for large enough n and k, it's approximately equal to 2nk squared. So, zooming way back out, computational complexity of this thing, if we have k vectors of length n, it's about 2nk squared flops. It's going to grow linearly in the length of the vectors and quadratically in the number of vectors, which in sort of a ballpark idea makes sense because we have this outer for loop that we're doing we're doing k times, approximately, right? And then this inner thing is also in some sense like a for loop. This is going to require order k work. It's going to grow as the number of vectors grows. So it makes sense that that's approximately k squared. And then, of course, each vector is length n. So any work that we do, we have to do n times. So just sort of gut check, it makes sense that this is right here. Yeah, so it's a little bit expensive. It's more expensive than some things, but really it's not bad. 2nk squared.